All right. So there's one big evaluation measure we still need to talk about. And then actually it's more than one. It's average precision and precision at rank, at a certain rank. They're interrelated, so we'll be able to talk about them both at the same time. We're also going to talk about precision recall curves as well. All right, so this is a long-standing evaluation measure, and the best way to actually get into it is to work from an example. And so what we can do is I'm just going to go ahead and we're going to show an example set of ranked results. And so remember, we have a query. It runs for and for this given search topic in our test collection, we actually know we believe we know what are the relevant documents. And we then can go look at the QRELs, these relevance judgments for this given topic, for a given document identifier, and look up whether it's relevant or not. So let's say, again, we've got ranked results, and you see you've got these doc nodes. And so in our case, we're going to see, yeah, we have LA something, blah, 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 and then LA, blah, blah, blah. So these are all documents from the LA Times. And we have, this is what our results file looks like. Note, our results file does not have a header. It's just the doc nodes and some other columns. But this isn't even, I'm not showing you really the ranked results format file. This is a other representation of it, so don't get those confused. And so yes, this is at rank 1, rank 2, 3, 4, 5, 6, 7, 8. All right, let's look at those first 8 now. And actually, I'll just go ahead and write 9 and 10 to make us all happy. Okay, so now we go and we look in our QRELs file, our relevance judgments. We know what the topic is, so it's one topic, so one query that's produced these. We go and look for that topic, we look up this document identifier, and we say, what do we have a relevance judgment for it? If we do, we know, in this case, for this collection, there are binary judgments. They're either relevant or not. I'll note right now that average precision, before I forget, average precision and precision at n, which is the notion of precision at a certain rank. We're going to define these in a moment. These are only for binary relevance. There has been some work to extend average precision for graded relevance, but it's normal use case. We always talk about average precision as binary relevance. So it's 0 for not relevant, 1 for relevant. All right, so is it relevant? So in this case, I'm going to say yes for my example, and then no and no. And then we got 2 relevant documents, and then no, no, yes. And then, by the way, it has to be no and no, because I'm going to say for this topic, the number of relevant documents in total is 4. Now, I want to really point this out to you. This is where a huge number of students get confused. They look at their results file, and they've got, say, 1,000 results for this topic. And they count up the number of relevant documents there. And they think that is the number of relevant documents for the topic. It is not. The number of relevant documents for the topic comes from the QRELs file, comes from the relevance judgments file. It's part of the test collection. It's not part of your run, not part of your system. It's part of the test collection. So you go into the relevance judgments file for that topic, and you can count how many documents have been found and recorded as relevant. That is the total number of relevant documents. So that we say R is the set of known relevant documents, not the set that you returned, the total known in the collection. And then we can take and say that's the number of them. All right. Please don't confuse the two. All right. Now we can compute P. I'm having trouble writing my at sign this morning. P at N. So this is precision at N, or precision at rank N. And it's very simple. We recall the concept of precision. We talked about it earlier in the term. Precision is the fraction of documents that are relevant. Okay, so of the returned documents, what fraction of them are relevant? And so by saying precision at rank N, what we're doing is we're saying up to this rank of all the documents returned, what fraction of them are relevant? So at rank 1, I have one relevant document, so 100% of my documents are relevant, and precision is a fraction, so from 0 to 1, so we get 1.0. All right. At rank 2, we now have 2 documents in our set to consider. Only one of them is relevant, so our precision at that rank drops to 0.5. Next up, 3 documents returned, one of them is relevant, so our precision drops at that rank down to 0.33. So it's of these 3, what fraction were relevant? And so it's as we're going down, what's the precision that we are seeing or have seen up to this point? Okay. Now we get to rank 4. Now we have 2 out of 4, which are relevant. So that's 0.5 again. Now we get to rank 5. Now we have 2 out of 5, and that gives us 0.6. Rank 6, we drop back down to 0.5. Then we go 0.43. Then we go 0.5. And indeed, I could actually keep calculating these, and I'm not going to bother, by the way. So I'm going to actually get rid of them off of my example. You could do that, and your precision at that rank would forever keep dropping because there are no more relevant documents in the collection. So this is one of those measures, precision at a certain rank, that is a little strange. Especially if you have a small number of relevant documents, it's really quite possible that you could pick a precision at rank like precision at rank 10. Usually, like, I want to compare systems and stuff, and the problem is no system, if you do precision at rank 10 and there's only 4 relevant documents, no system could ever get 100% precision at rank 10. It's impossible. The most they could ever get is 0.4. So yeah, that's one thing that you have to be really aware of sometimes with some of these measures, is that they might not make sense based upon your test collection. So anyway, I'm just going to continue this example where we go for the first 8, where we have ended up now achieving and finding all of the relevant documents. Now we can also write down the recall at a various rank. Okay, so again, this is just simply, we've made it this far. What fraction of all the known relevant documents have we found? So there's 4 in total. At rank 1, we found one of them. So our recall here is 0.25. We found a quarter of them. We've recalled a quarter of the relevant documents known. Now, it stays this way, of course, until we're going to find another one. And then, great. We finally found another one, and we go up to 0.5. We find another one, we go up to 0.75. We stay at 0.75. 7.5, and then we eventually get 100% recall. Okay. All right. That's pretty cool. You're like, why? Let me tell you. This is where unfortunately, I need a really big whiteboard like I would have in a normal classroom. I would leave this up and we would work and I would show you another display, I realize. What you're going to need to do is you're going to need to have this and be able to refer to it as I go along, because I have to erase it right now. So those are our precisions at a certain rank and our recalls at a certain rank. Those, we can view these graphically, okay? And so a very typical display is to put recall on the x-axis. It goes from 0 to 1. And to put precision on the y-axis. Okay. And what we're going to do is we're just simply going to go down that table I made on the previous board and draw the points. Okay. So the first point was at 0.25 and 1, and so we had a point there. The next one, the recall didn't change, but our precision dropped down to 0.5. The next one, our precision drops down to 0.3. Okay. Then, once we found our second relevant document, our recall now moves to 0.5, and our precision is at 0.5. Then we actually find another one, and this time it goes up to 0.6. Okay. I'm maybe exaggerating the view here for purposes. And then we stay at 0.7 and we go back down to 0.5. Then we go back down to 0.43. Then at rank 8, now we have found everything, and we end up at a precision of 0.5. So if we wanted to, you could say, well, at recall of 0, my precision is 0, because I haven't, maybe I could say I start here. If you wanted to, you could probably draw some sort of line that was to interconnect these guys. Let's get this right. And it actually goes, yeah, it does go up to 0.6 then. Comes down and goes back up. You can end up with these sort of sawtooth lines. Problematic about it, though, is the first point was here. It wasn't down here. In other retrievals, if you don't put relevant document at rank 1, absolutely, your first point will be 0. You will have a precision of 0 and a recall of 0. So it's kind of like that, doing things like that's not right. What does it really mean to draw these lines interconnectedness? Because it's not as though we have actually any recall values between 0.25 and 0.5 here, but we're drawing these lines. The lines would only be drawn in this circumstance because you wanted to see the order in which you put those points up there. The lines themselves would have no meaning. So let's get rid of them. That is definitely not the way we want to draw lines on a precision recall plot. All right. What is legitimate, though, is to think about those moments where we found another relevant document, because we get this general pattern where we've got a relevant document here, and then as we get a bunch of non-relevant ones, things decrease, and we're just staying through recall. And then the next time we find another relevant document, we get this point, then we get that point, and then things fall down, and then we get our last relevant document. So it's a lot better for us actually to think about our plot as basically something that looks like this. A bunch of rectangles. Okay. Now, so basically, we have a rectangle formed from whatever the previous recall point was and the precision. So for each of these. And so if we had, 10 relevant documents total in the collection, we'd have 10 of these little rectangles as we go from 0 to 1 in the recall. Now, one of the things that's interesting here is basically we can take this and you've got this rectangle here, and we could talk about its area. Again, area is height times width. And so this here, its height is 1 times its width is 0.25, and we get a 0.25 for its area. This guy has an area of 0.5. That's its precision, times by 0.25, and that's equal to 0.125. And we could do that for this and this as well, So we could calculate those. And then what we could do is we could sum up these areas. The idea being that the better a ranked result, the more area we should have. So the very best result that you could have as when you're doing ranked retrieval is you just have all relevant documents returned. And so your precision stays at 1 for the whole entire time until you reach recall of 1, and then you're done. So you could end up with a total area of 1. The poorer quality of your system, the lower this goes down. All right, the less area you will have, so to speak, under a curve where you're drawing the curves in these rectangular box fashion. So this area here is what we have. If we sum them up, we have what is called average precision. The way to think about the name is that we are taking the average of the precision at n at those ranks where we found a relevant document. Okay, so average precision is equal to 1 over the number of relevant documents. So this is the number of relevant documents. I'm going to sum up. I'm always out of space. I'm going to have to erase some stuff here. And so we go up to the number of results that we have in our ranked list. So if we had 1,000 results, we'd sum up to over 1,000. I is going to be our rank from 1 to whatever the total number of results that we have. And then we ask whether or not this document is relevant or not. And this is 1 if ith doc is relevant, it's 0 otherwise. So if it's relevant, it's a 1. We give it a value of 0 otherwise. Now note that otherwise includes the notion that an unjudged document, a document for which we do not know its relevance, we will assume it is not relevant, okay? So we will end up, this will be a 1 or a 0. It's 1 if it's been found to be relevant. It's 0 in all other cases. And then we just multiply this then. So this is like an indicator, the precision at I. So again, this is the precision at rank I. All right, so that's what average precision is. By the way, I want to note that once upon a time, the book explains average precision, but it doesn't have the formula for average precision in it. It's a small oversight. And so there was a set of students who one year who didn't attend lecture. And what they did instead is they went to Google, then they went to Wikipedia, and they actually copied the formula. They actually did a screenshot of the formula and put it in their report for average precision. And then they calculated everything using that formula. One, they didn't cite where they got this formula. They just took it. So they took this image from Wikipedia, and they should have actually said that they got it from Wikipedia, proper citation. It turned out that someone had actually put in the formula wrong for average precision. And so the students used the wrong formula in their reports and got things wrong because they didn't come to lecture. When I went back to Wikipedia, I was like, where did they get this formula for average precision? And I thought maybe Wikipedia, and I looked at, oh no, it's got the correct formula. I had to go into the edit history and see that, yeah, a couple days before I had checked, someone had fixed this mistake. So it had been existing on Wikipedia for a long time, actually, and these students fell prey to that mistake. Be careful about Wikipedia. It's usually quite good, but you should double check what's in there against other authoritative sources. Anyway, so that's average precision. We can think of it then as this area that's being produced. Let's look at that a little bit more. So these plots of precision and recall so we had a point here, basically, a point here, a point here, and a point here. And then we had some subsequent points on the plot. Now, one of the things that we know about precision and recall is that, in general, as recall increases, precision decreases. Now, we certainly saw in that small example that the precision went up at one point and then it went back down, okay? But in general, this is what we see, is that as recall increases, our precision will decrease. This is a general trend, a general sort of almost, you could say, law of retrieval. Of course, it's not always true, so it's not a law, but it's in general true. And what we end up doing when we want to actually plot these is that we say that our precision will be monotonically decreasing. So we can never go back up. And so the nature of this is what we do is we start with our drawings at the far rightmost point. We go back until we get here. We go up. We go back. Oh, I'm lower than that, so I'm just going to keep on going. Then I'm going to go up, and I'm going to go do that. And we're able to produce a curve. This is a precision recall curve. Now, what we will end up with is this notion that we'll have different topics, and we want to be able to look at one precision recall curve for the topics. And so you might have had another topic that maybe, let's say it has 3 relevant documents. So the first one is found, when we get the first relevant document, it's actually, it's only got a precision down here. The next one is found, and the precision is down to here. And the final one, unfortunately, was really hard to find, and it's down here. So this guy gets a curve that's like this. Okay. Now, we can draw all these sorts of curves for all sorts of different search topics in the test collection, and they will have different number of relevant documents for each search topic. So these recall points will be at different places. Well, the idea is to get one sort of average precision recall curve is that we take all of these in what are called interpolated curves, okay, and then we pick standard recall points, for example, like 0.1, 0.2, 0.3, and we just go on up. We draw a line up, and everywhere where we intersect these, that's the value of that precision recall curve that's interpolated precision at a given recall value. And then we go ahead and we just produce the new average. All right, and so we go here, we go here. If this was my point, I'll just draw some more points, whatever. And 0.3, we're going to end up with a value that's like this. So what we end up with, and then we can also do it here, and this will be the same. And we're able to produce some sort of curve, all right? And so we can produce an average curve by drawing these interpolated precision recall curves and then picking standard recall points and averaging the curves at those points. And that's how we make these precision recall plots that you might actually see somewhere. The textbook actually goes over those quite nicely, explaining that. I definitely like that. It's sort of, in many cases, a lost art about what's the way to do those. You will see very, very few precision recall curves anymore. But they can be a handy way to understand things. So you could have a system, you could have one system that behaves like this, and you could have another system, let's say, that behaves like this. Okay, so let's call this system A, and this is system B. What's interesting about this is it gives you a sense that as we start at the retrieval results, basically when we haven't recalled many of the results yet, what we can see is that system A is able to early on achieve high precision, but as it needs to find more and more documents, its recall falls off. So system A seems to be tuned towards being able to get relevant documents near the top of a ranked list, but overall it has trouble finding most of the relevant documents. Whereas system B does not start off as strong, but it has more staying power. It's better able to find those relevant documents, all right, with respect to, because again, with this low precision here, system A, for you to get out there, it means you're having to look at lots and lots of relevant documents. That you've found all the relevant documents at this precision with system B, which is higher, means that in total, to get to 100% recall, you had to look at fewer relevant documents. So from all of these points here, system B is better, but all of these points, system A is better. So at these recall levels, system A is superior, but at these recall levels, system B is superior. And again, superior is how many documents are you having to look at to find your relevant documents? What's your precision at those recalls? So these comparisons can be useful. You will not see them that much, but sometimes when you're trying to diagnose and understand a system, it might be helpful to make that sort of plot. The downside with these plots is that they all emphasize the notion that we have to be able to know the total number of relevant documents. This tends to have only been the case with smaller test collections. The web, we don't know really the total number of relevant documents. And it's rarely actually the case that we need to know that. Usually what people on the web are looking for is, I need enough information to solve my problem. And I'm going to issue a series of queries until I find that information. And I'm going to tend to only look at the top of those ranked lists of those results that I look at. And that's why NDCG is a dominant evaluation measure in the web. It reflects that, okay? It reflects that the top of the ranked list is most important to the users. It does not, NDCG does not have any notion of the total number of relevant documents. You can use it without knowing all of the relevant documents. Average precision requires you, because again, it's going to average over all the known relevant documents. You need to know what the total number of relevant documents is. To make a precision recall plot, well, you have to know the total number of relevant documents ever to draw a recall. So when we go to the web and we go to large collections where we don't really know the total number of relevant documents, these plots no longer make sense for us. Therefore, average precision no longer can be used. Things fall apart. What people, if anything, they use precision at rank 10 or precision at rank 5. That's a measure where we don't need to know the total number of relevant documents in a collection. It gives us a sense of what fraction of the top documents are relevant. And that's a very interpretable number. But again, people really like a better way to distinguish runs is to use NDCG. All right, so yeah, I just want to double check my notes here. All right, some points about average precision besides what I've said, and I'll write them on the board. So AP, average precision, is recall sensitive. Okay. Because it pays attention. It's a measure that pays attention to all the known relevant documents. To score well, you actually need to overall do well on all those relevant documents. So it's not just, it might have precision in its name, but it's paying attention to all the relevant documents. And so it's actually quite recall sensitive in comparison to something like NDCG. I would say, this works well as a sort of standard measure that everyone will understand. And it gives good feedback to machine learning methods for ranking. So they need to measure how their quality is, and average precision seems to work quite well. Unfortunately, again, you go to the web, what does it really make sense to be talking about average precision in this regard? It's problematic. I will say also average precision, people have tried to do this, but I don't actually feel that it has any plausible user model. So there's no plausible user model that really goes along with it. And, so I've already said that people tend to report precision at rank N. I think the sort of wrapping up our evaluation measures, an important thing to note is that, that we often need multiple measures to see the whole picture. All right, so one measure, one single number is rarely enough. You'll want to look at it from lots of different angles. When you work at a company, you'll have the problem where people will want to pick whichever measure their techniques are working well on, and they'll ignore the other measures. That's wrong. You need to pay attention to multiple measures. The other thing being is that different applications demand different measures. So if you are a lawyer working on a case, recall is really, really important to you. You want to find all the case law that exists. Okay, you can't just get by with finding a few examples in the case law. You need to find them all. Meanwhile, though, like you're in a bar and you want to look up a little piece of factoid information, you don't need to find every web page that tells you the height of Mount Everest. You just need one authoritative source to tell you. And in fact, you might even not need an authoritative source. You just need a source to get on. So different measures for different applications. If you're an e-commerce website, your measures of success are probably going to involve something that actually has to do with leading to profit, and not just, you know, user satisfaction in their searches or their ability to find products. You probably are actually considering search as a tool to drive profit. And so for all we know, you are actually working to manipulate the search results so that people tend to be directed towards, in-stock products. They tend to be directed towards higher profit margins, all sorts of things. It's not what the user necessarily wanted. It's what you can get people to end up buying and feeling good about their purchases so that they'll come back and make more. There's a whole bunch of things. So you need to be prepared to use different measures, to craft your own, create your own models, calibrate them, validate them. The application matters, and we have to wisely use our measures depending upon what our application is. Average precision. Oh yeah, I have a collection where I know where the relevant documents are and we're very recall focused. Okay. Oh, it's very web-like and people are not going to be searching very long. Oh, something more like NDCG, or oh, I just want a sense of the really, what are the top 5? Maybe precision at rank 5, So different measures tell you different things, and you have to pick and choose wisely, and as well often use multiple measures to see overall what is actually happening with a search system.